Today we're going to be talking all about matter and energy. So what is the nature of matter? We have gold and we have mercury, and on an atomic level they look pretty similar, but on a macroscopic or with the invisible eye level they look very different. So chemists are interested in the nature of matter and how this relates to its atoms and molecules. So why is matter the way it is, and how does this connect to that internal structure? So we can explore the macroscopic word, macro meaning large, which is what we can see. To understand the microscopic worlds we cannot see, keeping in mind micro means small, so these words make a lot of sense. We write symbols to describe these worlds. So let's talk about water. We're all familiar with water. So to a chemist, a macroscopic view of water might be this iceberg right here. It's huge, we can easily see it, and we know that it is frozen water. We can also have a symbolic view of water where we write water as H2O. That is a symbolic representation of water. But we can also have our microscopic view of water where it is made of that one oxygen, this red in the center, and the two hydrogens off to either side. Water really does look like little Mickey Mouses, which I find adorable. But it is a microscopic view. So chemists are viewing the world in these three ways at all times. So this brings us to the kinetic theory of matter. The kinetic theory of matter states molecules are always moving, and this is known as the kinetic theory of matter. We measure this kinetic energy with a thermometer as temperature. The greater the material's internal energy, the higher the temperature of that material. Heat is energy flow between objects of different temperatures. Heat and temperature are not the same. That's one that always gets students confused, so you might want to star that one in your notes for yourself, because temperature is just what we measure with a thermometer, but heat is more about energy. And Brownian motion describes how visible particles are seen moving due to invisible molecules bumping into them. So, for example, if you've ever seen sun coming through the window and you've seen those particles moving through the air, so that's dust and other things. It's something we can see, but they're moving due to the invisible particles in the air that you can't see bumping into them. So matter consists of atoms and molecules. Everything in the world consists of atoms and molecules. And we divide that matter into three different states of matter primarily: solid, liquid, and gas. How those atoms and molecules behave in each of those states of matter is different. You will notice in the solid, the atoms and molecules are all condensed together and they are all neatly arranged one on top of each other. There is very little movement. They create a shape and stay in it. Meanwhile, in liquids, you can see that they have some space, they're not as nearly organized, but they still kind of take up a defined sort of space. Meanwhile, in the gas, our molecules can be moving all over the place and take up as much space as they possibly can. So let's talk a little bit more about those states of matter. So blank states of matter have a rigid shape, fixed volume, and the external shape can reflect the atomic and molecular arrangement. There's very little space between atoms, little energy, and it is the most dense state of matter. There is an exception, but for our purposes, it's the most dense state of matter. So what am I describing? That's right, a solid. What about this one? So this state of matter would have no fixed shape, may not fill a container completely. There is space between molecules. It has a medium energy and a medium density. So that would be a liquid. And our last one, it expands to fill their container. There's a lot of space between molecules. It's super high energy, but is going to have a very low density. which means I'm describing a gas. Now, you're probably familiar with solid, liquid, gas as a state of matter, but another state of matter you may not have heard of before is plasma. And plasma is an electrically charged gas. And the most common example of plasma is the sun or any other star. They are constantly in the state of matter plasma. This is not to be confused with the plasma you may have heard about being in your blood. That is something completely different and is not actually in the state of matter of plasma. So once you know the states of matter, this brings us to phase changes, and you need to know the names of these phase changes. So phase changes are when you move from one state of matter to another state of matter, and we have different words depending on what you're doing. So if you have a solid and you go to a liquid, that's melting, but going from a liquid to a solid is freezing. You probably knew those. Now if you have a liquid and you turn it into a gas, that's called vaporization or vaporizing. And if you have a gas and turn it into a liquid, that's called condensation or condensing. Most students know these 4 words, but if you don't, you still need to learn them anyway. Now, the 2 that students often don't know is if you have a solid, and some solids can go straight to gases without becoming liquids in the middle, that's called sublimation. And similarly, if you have a gas and it's going straight to a solid without stopping in a liquid, we call that deposition. I think about it as depositing, so it's depositing a solid. Once again, you do need to know these names. So we can put phase changes into what is called a phase change diagram. They will always kind of have this Y shape in them. And a phase diagram is a representation of a phase transformation and also the different phases and conditions of transformation of matter. So what they're showing is that at different temperatures and different pressures, you will have different states of matter. They always go solid, liquid, gas. The solid will always be the first group, the liquid will always be in the middle of the Y, and the gas is always going to be down in this bottom part. Anytime you are on the lines, that represents a phase change occurring. So the line between solid and liquid is melting and freezing. The line between liquid and gas is vaporization and condensation. And the line between solid and gas is sublimation and deposition, just like we talked about. You will also notice that where all 3 come together, we refer to that as the triple point. And this very end where the line stops, we refer to that as the critical point. Now at 1 atm of pressure, which is normal conditions, our pressure is typically about 1 atmosphere. Where 1 atmosphere crosses those lines, that's where we find our melting point, solid to liquid, and that's where we find our normal boiling point from liquid to gas. Once again, normal meaning 1 atmosphere, but melting could happen at different places if we change the pressure. So the phase change diagram of water looks a little different. You can see that its Y is much more spread open than the Y in a typical simple material. So water is one of the few substances whose solid state is less dense than its liquid state. Most substances' solid phase are more dense. The fact that water does that is actually one of the reasons our planet is able to exist the way it does. It's really cool. I recommend you look into it. But that difference causes the water's diagram to look differently. So let's do a little practice with these phase change diagrams. So you're asked, what state of matter does point G represent? So we find point G here on our graph, and we know that it represents a liquid. Number 2 asks us, what do we call point B? So we find point B here, and we see it's where all 3 lines come together, so we call that our triple point. Number 3 asks us, what do we call moving from point G to point A? So we already said that G was a liquid and A is a solid, So if we go from G to A, that means we are going through freezing. And number 4 asks us, what substance could this heating curve represent? One of the things I quickly noticed was how wide the Y was in it. So I instantly said that it could have represented water. So in addition to phase change diagrams, we also have phase change graphs. Phase change graphs are different in that they have this stair-step shape instead of our phase change diagrams we just saw that have more the Y shape. The phase change graphs show us what is happening at different energy outputs instead of different temperatures and pressures. So earlier when we talked about kinetic theory, we discussed kinetic energy. One of the things we discussed in that was how do we measure kinetic energy? And if you'll look back in your notes, you'll see that we measure it using a thermometer because we measure it in terms of temperature. Now, as far as these graphs are concerned, they are representing kinetic energy and potential energy. The kinetic energy is increasing on the sloped lines. So when we are in our phases, solid, liquid, gas, or when our kinetic energy is increasing. Meanwhile, our potential energy increases during phase changes or the flat lines. So when phase changes occur, our potential energy is increasing. So let's practice reading a phase change diagram. So 1 asks us which letter represents the liquid phase. So keep in mind that our phase changes, our states of matter are our sloped lines. So they always go solid, liquid, gas. So for ask what our liquid phase is, we're going to say C. Number 2 asks us what is the melting point of this substance. So our phase changes are the straight lines. So in this case, B and D. Well, you should know by now that melting is when you go from a solid to a liquid. So that means we are looking at B. Number 3 asks us which represents sublimation. Now this was a little bit of a trick question because sublimation isn't actually on there. Remember, sublimation is when we go from a solid, which we know to be A, to a gas, which we know to be E, but we don't see any line connecting them, so there's not a letter that represents it. 4 asks us what letter has the lowest energy. That's going to be A because solids have the lowest energy. And 5 asks us where is kinetic energy increasing. And you will remember that kinetic energy increases on these slopes. So it's increasing on A, C, and D. This brings us to an interesting property called density. So density is the mass per unit volume. And its equation is D equals M divided by V. Density is measured in the units of grams per centimeters cubed or grams per milliliter. Units you should both be familiar with now. We're just putting them together. So density is a physical property. Now you can see at the bottom, I have put my friend what I call the density triangle because you can be asked to be solved for the density, the mass, or the volume. All 3 different parts of the equation. Now I know some of you have trouble switching equations around to solve for the part that you don't know, so the density triangle makes it easy. You simply cover up the part of the density triangle you're trying to solve for, and then the other parts tell you what the equation is. For example, if I'm trying to solve for density, I cover up the D, and I can see that I have mass divided by volume. Similarly, if I'm asked to solve for volume, when I cover it up, I can see that I have mass divided by density. And if I'm asked to solve for the mass, I can cover up the mass, and I see that I have density times volume. So it's just a handy little trick to help you flip the equation around. Now, how would you determine the density of a metal? There's quite a few different ways. Regardless of the method we choose, we're going to have to get its mass. Now you know from your lab equipment activity that you're going to use a balance in order to determine the mass of something. Pretty straightforward. But you might be wondering, well, I know the other part is either centimeters cubed or milliliters. How am I going to get either of those? So you could get the volume of the metal. If it's regularly shaped, you could use a ruler. and measure the length, width, and height in centimeters and multiply those three numbers together to get your volume. Then you just divide mass by volume. But say your piece of metal isn't regularly shaped, it's a chunk of gold. Then we can use the graduated cylinder. If we fill the graduated cylinder with a known amount of liquid, say 50 milliliters, I can drop that chunk of gold in there, and the amount the water raises, say it's 5 milliliters, tells me the volume of my piece of gold, getting me my milliliters. Once again, I just divide mass by volume in order to determine the density. Now let's try some math problems. I want you to round all answers to the 100th place, so that means 2 decimal places. So I want you to pause this video and try and answer these 3 questions on your own. Come back when you're done. All right, so you're asked, what is the density of an object that weighs 40 grams and has a volume of 1 milliliter? You got the correct answer if you got 4.00 grams per milliliter. You would have gotten that by dividing the grams by the milliliter number. Our next question asks us what is the mass of an object with a density of 0.99 grams per milliliter and a volume of 12 milliliters. Correct answer for this one would have been 11.88 grams. You would have gotten this answer by multiplying the density times the volume. And our last question asks you what is the volume of an object with a density of 1.23 grams per milliliter and a mass of 50 grams. You would get this answer by taking your mass and dividing it by your density to get an answer of 40.65 milliliters. How did you do? We're going to be doing some more density practice, but if you didn't get this right, I recommend rewinding and watching the earlier part again. Now, before I mentioned density was a physical property. So what is a physical property? So physical properties are things like color, melting and boiling point, any phase change really, how they smell, their odor, their shape, and their density, like I always mentioned. They can also be the phase of matter, like solid, liquid, or gas. So these are physical traits that something has. We would say something is a physical change if it can be observed without changing the identity, that molecular atomic structure of the substance. So some examples of physical changes would be boiling of a liquid. We can boil water and it's still water. The melting of a solid. I can melt an ice cube and it's still going to be water. Dissolving a solid in a liquid to give you a homogeneous mixture, also called a solution. If I take water and I dissolve salt in it to get salt water, I still have salt and I still have water. They've just been dissolved into each other. A phase change is also going to be a physical change. So if I go sublimation, for example, is just going to be a physical change. On the other end, we have chemical properties. And chemical properties are a property or characteristic of a substance that is observed during a reaction in which the chemical composition or identity of the substance is changed. So some examples of this are heat of combustion, flammability, its ability to catch on fire, toxicity, how kind of poisonous is it to people and things, reactivity, how much does it react with other elements, rusting, I'm sure you have seen iron turn orange, and that is rusting, and it is a chemical property. So as far as chemical properties and changes, the burning of hydrogen in oxygen gives us H2O. This is a chemical change or a chemical reaction because I can't get those two things back. So the transformation of one or more atoms or molecules into one or more different molecules. So we take something that used to exist and had its own properties, and we have put them together to create something that has new or different properties. And this is a chemical change. So some sure indicators of a chemical change. Heat being produced. Something was a nice room temperature and all of a sudden it gets really hot. I do not mean because you put it over a fire. I mean all on its own it gets hot. Light is produced. Out of nowhere it starts to glow a bright color, for example. Effervescence, also known as bubbling, and this means a gas is produced. This is not to be confused with boiling. If you put water over heat, it's going to start to get bubbles, but we call that boiling. I mean, you add one liquid that's not bubbling to another liquid that's not bubbling, and it starts bubbling. That is effervescence. And odor being produced. It smelled like one thing, you mixed it with something else, and it started to smell different. A precipitate, another vocabulary word for you, which is a solid formed by mixing two liquids together. And sometimes color. This one always gets students. The color of something is a physical property. And if I add food dye to something, even though I've changed its color, I have not changed its chemical properties. I've just added a color to it. But meanwhile, we're going to be doing some labs where, example, you add a clear liquid to another clear liquid, and it will create something that is bright yellow. That's an example of a chemical change because you took clear and clear and it made yellow. So color is tricky. Always make sure you're on the lookout for it. So let's compare physical versus chemical properties. So some examples. Melting point. That is a physical property. Phase changes are always physical properties. Flammable, whether it can catch on fire or not. That is a chemical property. Density, I've mentioned it twice now. It is a physical property. Now, I didn't mention this one. Magnetic, so whether it can attract other metals or not. That is a physical property. And tarnishes in the air. So tarnish is a lot like rust. And what category did I say rust was under? A chemical property. This is not to be confused with physical versus chemical changes. So rusting of iron is chemical. Dissolving in water is physical. The burning of a log is chemical. Keep in mind, once you have burned a log, its properties are now completely different from when you started. The melting of ice is physical because it is just a phase change. Now, grinding of spices is not something we really talked about, but if you think about it, you have something you've crushed into smaller pieces. Have you really changed anything about it other than the size of the pieces? No, you haven't. So that means it's physical. So this brings us to our matter flow chart that's kind of combining all of these things together. So we have matter, what we opened our presentation with. And you can ask yourself, can it be physically separated? Could you grind it, cut it, do something? If the answer is yes, that means you have some sort of mixture. If the answer is no, that means you have some sort of pure substance, like an element on the periodic table. When you have a mixture of something, you're asked, is the composition uniform, meaning the same throughout? If the answer is yes, you have a homogeneous mixture, also called a solution. If the answer is no, you have a heterogeneous mixture. Now, if you ended up with a pure substance, you can ask yourself, can it be chemically decomposed? Can we break it down in a chemical way? If the answer is yes, that means you have a compound, like sodium chloride, NaCl. If the answer is no, that means you have an element off the periodic table, like the ones you memorized over the summer, and we cannot break it down. So these are all words that you need to know and make sure you know them. So let's talk about them a little bit more. A pure substance is a substance with a constant composition, a pure element or a pure compound. An element is a substance that cannot be decomposed into simpler substances by chemical or physical means. It consists of all of the same type of atoms, and we represent it with that elemental symbol you were asked to memorize. And a compound is a substance made of two or more different elements that have been chemically combined. This is represented by a chemical formula, which we'll get more into later in the semester. And it always has definite proportions, meaning it always has the same amount of the stuff in it. As far as types of mixtures are concerned, keep in mind a mixture is a combination of two or more pure substances physically combined. An alloy is a mixture of metals. It gets a special name, but it's just two or more different metals that we've mixed together and then let cool to become a new metal. Down here, you can see two different types of mixtures. We have a heterogeneous mixture, and you can see it is not the same throughout. We can visibly see the different types of elements that are existing in this rock. Meanwhile, a homogeneous mixture is the same throughout and is a solution. Apple juice is usually made of apple juice, some water, and a bunch of other things, but you can't see them. It just creates the one amber-colored liquid. Now, based on what you've learned, I want you to label the following as an element, compound, solution, alloy, or heterogeneous mixture. Pause this video and come back when you're done. So lemonade, we can't see the separate parts anymore. We call it a solution. Sodium chloride is composed of sodium and chlorine, two different elements, making it a compound. Gold is an element straight off the periodic table. Steel is a mixture of different metals, making it an alloy. Pizza, we can see the different parts, the crust, the sauce, the cheese, the pepperoni. We see all the different parts, making it a heterogeneous mixture. Sulfur is also an element straight off the periodic table. And oil and water don't mix together, they stay separate, making it a heterogeneous mixture. And last but certainly not least, I want you to label the following pictures as an element, compound, or mixture. Each shape is a different element. Shapes touching each other represent a chemical bond. So pause this video and come back when you're done. All right, so in box number 1, we had only one shape, making an element. In box 2, we had two shapes, but they were all touching each other, making them a compound. In box 3, we had two different shapes, but they weren't touching each other, making it a mixture. And in our final box, we have kind of a combination of boxes 2 and 3. And it is also a mixture. It has compounds in it, but it also has other things, making it a mixture. Woo! That was a lot. If you're struggling with anything, you can always go back and rewatch these parts or bring your questions to class. Look forward to learning with you.